All right, next we're going to talk about another distribution, which is called the exponential distribution. All right, so let's consider to introduce this, we're going to consider a one-dimensional Poisson process, which we've seen before. So let's consider a one-dimensional Poisson process with intensity lambda. And this is a Poisson process on the positive real numbers. And we're going to call hits arrivals, okay? So call the hits arrivals. So remember, in the original introduction of the Poisson process, we had a two-dimensional area, and we imagined throwing points down, and we called the scatter of points hits, and we were counting how many hits occurred in any given region. What we're going to do for this is we're going to assume we have just a one-dimensional process from 0 up to onward. And we're thinking about, okay, we're thinking of this as times. Time is positive. And we're thinking about these as the arrivals. So the hits in this process are the times at which certain events occur. So in particular, we're going to define n sub a for a given set A. So for a subset of the non-negative numbers, n sub A is going to be the number of arrivals that occur during A, so to speak. So, for example, if this is A, if we define A as some set A to B, then the number of arrivals that are occurring in this range is just, well, it would be 3. Uh, it would be 3, okay? So in particular, for example, the number of arrivals between A and B above is 3. So then by the Poisson, so this is a Poisson process. What are the assumptions of a Poisson process? It's that the number of events that occur in a given region are Poisson with intensity lambda times the size of the region, and non-overlapping. The counts in non-overlapping regions are independent. So in this case, for any s less than t, so if we're looking at an interval, the number of occurrences within the interval is Poisson with intensity lambda times the size of the interval, which is just t minus s. Okay. And we're going to define a random variable called capital T to be the infimum, or you can think of it as the minimum, but it's it's the first time at which, it's the first time t at which the count reaches 1. So it's the time of the first arrival. So up here, this here would be this x, this first arrival would be equal to t, right? it took us this much time to get to the first arrival. And so this is the mathematical way to write that, because it's accounting. It's a process that the number of arrivals that have occurred since zero is only going up, right? If we count all the arrivals that have occurred, every time an arrival occurs, the number ticks up, and then it stays the same for a while, and it ticks up again, ticks up again. So the number starts at zero, and then at some point it hits one, and that's what we call the time of the first arrival. That's what we define as this random variable t. So then the question is, what's the distribution of t? So there's a couple of ways we can do this, but we have everything we need to be able to do it. So what's the distribution? So the first method we're going to do, method one, is we're going to just calculate the cumulative distribution function pretty much directly. Let's calculate the survival probabilities first. So what's the probability that the time t is bigger than some value little t? So let's make clear that t is going to be just a constant bigger than or equal to zero. Probably the waiting time is the first arrival is after t, right? In order for the first arrival to be after t, we need to have no arrivals between 0 and t. Having no arrivals between 0 and t is equal to saying that the number of arrivals between 0 and t is 0, right? But we know by assumption that it's a Poisson process, so the number of arrivals between 0 and t is Poisson with intensity lambda t, and the probability that a Poisson takes, so in particular then, the mass function is lambda t to the k e to the minus lambda t over k factorial. Well, in this case, k is 1, k is 0. So lambda t to the k is lambda t to the 0, that's 1. K factorial is 0 factorial, that's 1. So this is e to the minus lambda t. Those are the survival probabilities, and from that we can immediately define the cumulative distribution function. It's the probability that t is less than or equal to t, 1 minus e to the minus lambda t. And the density, so 1 minus e to the minus lambda t, is continuous and is differentiable. So we can get the density by taking the derivative, as we saw before. As long as the distribution function is well behaved, we can just take the derivative to get the density. And this derivative is lambda e to the minus lambda t. This is for all values of t bigger than or equal to 0. That's one way to do it. What's another way to do it? So another way to do it would be to use the infinitesimal approach, is to say, let's imagine that, so we want to derive the density directly. And the way that we're going to do it is we're going to say, well, if we knew the density, then what is the density? So we calculate probabilities of t by integrating f of t dt, right? So f of t dt for a small value of dt, right? This is approximately, so I should say approximately, but the approximations are equal. That's essentially what calculus is all about, is a study of infinitesimals. So if we take these infinitesimals, make them very, very small, these approximations become exact. So this is a way to do things that is a little informal, but it also can give you some intuition. It's really a matter of what you find um, more intuitive to do, right? So there's no, I wouldn't say there's a right or a wrong way to do this. It's really up to you. Um, and it's up to what makes sense to you. Okay. So you don't have to master both approaches. It's really about picking what works for you. So now this is saying what's the probability that t is bigger than t but less than t plus dt. So what does that mean? Well, what that means then, the only way for that to happen is that we have to have no arrival before time t. So there's nothing that happens between 0 and t. And we have to have exactly one arrival, or at least one arrival, between t and t plus dt. But if dt is really small, which we assume it is, the probability of having more than one arrival is going to be going to be much, much smaller than having one arrival. So we can just treat it as having exactly one arrival. So this is now probability that the number of arrivals between 0 and t is 0. And so it's the event, it's this event, and then the event that there is, let me exclude this point here, there is exactly one arrival between t and t plus dt. But notice that these are non-overlapping. 0 to t does not overlap t and t plus dt. They're not overlapping. Means that by the Poisson process assumption, these counts are independent. So since these counts are independent, we have a product of the probabilities. And the product of the probabilities, and each probability itself is from a different Poisson distribution, right? N0t, we already know, is Poisson lambda t. And n from t to t plus dt, well, that's Poisson lambda dt, right? It's just the width of the interval. Clean this up a little bit. So probability that no arrivals in the first t units of time, we've already calculated that before. That's e to the minus lambda t. And the probability of exactly one arrival from a Poisson lambda dt, well, that's lambda dt to the power 1, e to the minus lambda dt over 1 factorial. Okay, so now how do we do this? What we're going to do is lambda dt, well, let me just clean it up. Lambda e to the minus lambda t plus dt dt. And the dt is taken to be extraordinarily small. And so as long as dt is small, this is e to the minus lambda e to the minus lambda t dt for small values of dt, which we always assume. And so the density, we recover the same exact density, okay, as we did above. Okay, so this is the density of t, and this is the definition of what's called the exponential distribution. With intensity. lambda. And we write this as T is exp lambda. Okay. So the way that we derived the exponential was through it's the waiting time of the first arrival in a Poisson process. And generally speaking, the exponential distribution is used to model waiting times. And it's used to model them in a specific sense. And we'll see some examples of where the exponential distribution comes up as we go along. Here we've derived it in the case where we have a generic lambda, a generic intensity lambda. What I want to do here is let's define a new random variable x. Let's define it to be lambda times t. So we're scaling t by its intensity. Okay. Then x has the x in this case has standard exponential distribution. And standard in this case is what's called having unit intensity 1. Okay, so we could derive this. We don't have to just take, you don't have to take my word for it. If we define x in this way, what is the distribution of x, right? The probability that the random variable is less than or equal to x. Well, x by definition is lambda times t, right? And lambda is a non-negative, so we can just move the lambda over, and this is the probability that t is less than or equal to x over lambda, which is 1 minus e to the minus lambda, evaluated at the argument x over lambda, so it's 1 minus e to the minus x, right? So this is the CDF distribution function of the exponential rate 1. And the density of f is e to the minus x. Okay. So that's the definition. Okay. Now, the exponential distribution has some pretty significant properties and is oftentimes used in certain applications where we talk about failures of components. Okay, so we think about failures as being rare events. So you might be thinking about when the light bulb's going to go burn out, or when a machine is going to die, or need replacement, or need repair. So let's imagine we have we have a machine with 2 components. And let's assume that, let's let T1 be the time until failure of component 1. T2 is going to be the time till failure of component 2. And let's assume that T1 is exponential with intensity lambda 1. T2 is exponential with intensity lambda 2. And let's assume that T1 is independent of T2. What is the probability that component 1 fails before component 2. So this event, component 1 failing before component 2, this is the probability that the failure time of T2 is greater than the failure time of T1. Because if sorry, the T2 is bigger than T1, the failure time of component 2 is bigger than the failure time of component 1. How do we do this? Well, we have two random variables. And so generally speaking, we like to fix one and use conditional probability. So law of total probability. Integrate over all possible values of the failure time of the first component. So probability that T2 is bigger than T1 is probability that T2 is bigger than T1 given that that T1 is a specific value times the probability that we approximate as FTDT, right? And we're doing this in infinitesimal terms. Well, once we've fixed the value, once we've conditioned on T1 being a specific value, we can substitute it in on the left side here. And we have the density of T1. And then by independence, we can remove the condition because there's no dependence on the left side of T1 anymore. And T2 and T1 are independent. And then the probability that T2 is bigger than T is e to the minus lambda 2. See? Lambda 1, e to the minus lambda 1. See? Let's pull the lambda 1 out. Let's look at this and realize that this here is the component of an exponential. This is the main component, what's called the kernel of an exponential with rate lambda 1 plus lambda 2. What's it missing? It's missing the intensity. So we just have to multiply by the intensity and divide by the intensity. Okay. So if I multiply by the intensity, and then I divide by the intensity, what I'm left with is I'm left with something in the integral that has to integrate to 1. And so my answer is lambda 1 over lambda 1 plus lambda 2. In general, a nice property of exponentials is that if we have T1 through Tn independent exponentials with rate lambda I, respectively, then the minimum of these random variables, the smallest failure time, the time to the first failure among all the failures, is also exponential. Its intensity is the sum of the intensity parameters. So I'll leave this as an exercise. There's a few ways you can do this. One of the things to think about is, okay, why would that be true? Or how could this be true? Well, one way to think through it is these are the failure times of these are the arrival times of independent Poisson processes. And you can superimpose those processes on top of each other and you get another Poisson process. And then that Poisson process will have a first arrival time, which would be the minimum of all the arrival times of the component processes, and use the superposition property to get the intensity of that exponential. So that's an interesting way to get it. Another way is you can actually just calculate it directly by realizing that in order for the minimum to be above a certain value, all of them have to be above a certain value, and they're all independent of each other. So you can calculate component-wise the probability that each one is above a certain value, and then you multiply them together by independence, and you're going to get something, and you'll derive the distribution from that. Okay. But I'll leave that as an exercise, a few ways to do it. Okay, there's one other property that is really important about the exponential, which is called the memoryless property. Okay, so let's let t be exponential, rate lambda for some positive value of lambda. Let's consider two s and t bigger than or equal to 0 and consider the probability. So the question is, what's the probability that t is bigger than or equal to s plus t, given that it's already bigger than t? So here's the question. T and s plus t. So our question is this. We've already weighted t units of time. What's the conditional probability that we weight actually s plus t units of time, given that we've already weighted t units of time? Okay, well, let's try to calculate this. Well, this is just a conditional probability. So it's the probability that t is bigger than or equal to s plus t, and t is bigger than or equal to t. Okay. Okay. Divided by the condition, probability of the condition, which is probability that t bigger than or equal to t. Well, in order for t to be bigger than or equal to s plus t and t to be bigger than or equal to t, that's really just one condition, because s plus t is strictly bigger than t. So if you're bigger than s plus t, you're bigger than t. And then this is probability that t is bigger than or equal to t. Okay. Well, in the exponential, probability that t is bigger than or equal to some value, let's say u, is equal to e to the minus lambda u. So in the numerator here, we have e to the minus lambda s plus t. In the denominator, we have e to the minus lambda t. Okay, but now the e to the minus lambda t's are going to cancel, and we're going to be left with e to the minus lambda s, which is equal to the probability that t is bigger than or equal to s. So what's the moral of the story is that once we've weighted t units of time, we're asking what's the conditional probability that we have to weight an additional s units of time or more? Well, it's just the probability that we originally had to weight s units of time, right? So this is what's called the memoryless property, because what it's saying is that it doesn't matter how long you've waited so far. If the question is conditional on having waited so long already, what's the distribution of how much longer I have to wait? Well, the memoryless property says it doesn't remember how long you've waited. The distribution of how much more time you have to wait is the exact same as the original random variable. We saw this property also for the geometric distribution. The geometric and the exponential are the only distributions that have this property. geometric being a discrete random variable and exponential is continuous. So given that t is bigger than some value t, the residual lifetime, which is how much more time we have to wait, defined as t minus t, is still exponential with rate lambda. Exponential distribution is the only non-negative continuous random variable that is memoryless. So suppose the light bulb. So I'm not going to write this down, but what's the moral of the story then is, okay, suppose you have a light bulb whose lifetime is distributed as exponential with rate 1/200. So for the exponential distribution, the moments, calculate those a bit later. The mean of an exponential with rate lambda is 1/lambda. And so the mean of exponential rate 1/200 is 200. So given that the bulb still works after 800 hours, how much longer do you expect it to work? It's 200 hours. Whether or not this is a good assumption is, you know, in many cases, it's not a good assumption. In some cases, it is. One last comment that's important to make on the exponential is that we have assumed, so in our choice, so our convention is that lambda, so sorry, there are two different ways to parameterize the exponential. We've chosen one where lambda is a rate or it's an intensity. So it comes from the Poisson interpretation of rate. You expect a certain amount, certain number of occurrences per unit of area or per unit of time. So in this case, if t is exponential lambda, we have that implies density of lambda e to the minus lambda t. Another interpretation is you take theta and you make it be the mean parameter. So you say, how much time do you expect to wait? So in this case, sometimes it's written. So tx, so different authors use different conventions is my point. T exponential theta in this case would be f of t is 1/theta e to the minus t over theta. T is bigger than or equal to 0 in all cases. Okay. So these are two different ways of doing it. They're not the same, right? They have very different meanings, and we have to be careful not to mix them up. In this class, when I talk about it, I will always talk about this case. This is the more natural case. In some and this is what you'll see in most probability textbooks. But some statisticians will prefer using the mean parameter because statisticians are focused on means more often. But don't get confused. And it's always good to make sure that when we specify a distribution, we specify the probabilities or the densities or something, because you will find that some authors would write the same exact notation. T is distributed exponential lambda, T is distributed exponential theta, mean two very different things. So do be aware of that there are two different parameterizations. Of course, they're mathematically equivalent, that you can go from one to the other just by realizing that theta is 1 over lambda, or lambda is 1 over theta. But we have to be careful that we're agreeing on the convention when we're doing this.